Okay, so we'll start the session in 1 or 2 minutes. I'll wait for if one or two some more students join. Okay. Okay, so we'll start the session. So today, I hope you guys can see my screen. Yeah. So I'll switch out the video so that we get proper video after this. Yeah. Yeah. So hello everyone. Um, Today we are going to discuss about some of the assignment questions and kind of what we have seen in the week 5 lectures of the course that is Watershed Hydrology. I'm Balram Shah. I'm the PMRF TA for this course that is Watershed Hydrology by Professor Rajendra Singh from IIT Kharagpur. So I'm a PhD scholar at Interdisciplinary Center for Water Research at, at ISC. So with this, we'll start the session. So, what we have studied in this week 5 lectures are we have seen that what is hydrograph and what are the factors that affects hydrograph. Then we have also seen what is unit hydrograph and so on. So with those, we'll start with the questions. Okay, before moving on to the questions, let me. Okay, I'll share it from here. So I'll share it from here itself. Yeah. So in this week lectures, what all we have discussed? We have discussed what is hydrograph, then what are the factors that affects hydrograph, right? And then we have we have seen what is unit hydrograph, what are the key elements of the hydrograph, and then how we can separate the base flow. So there are several methods for base flow separation and so on. So all this will uh, go through some assignment questions, kind of assignment questions, and Okay, so we'll start with hydrograph. So before moving on to the hydrograph, I'll just reiterate one thing that we have studied before. So we have studied about hydrograph, right? Can anyone tell me what is hydrograph? So all this and these are we have studied before. So hydrograph is the plot between rainfall intensity versus time, right? So what we have seen in that, it is something like this, right? So let's say if I am denoting the rainfall intensity by I and time by t, let's say, obviously it will be in centimeter per second or meter per second, something like millimeter per second, something like that, right? So, and plot will be something like for each of the time, let's say if it is some hours, then it will be something like this, then it will keep reducing, something like this, right? So we also have seen that okay, let's change the color for this. Yeah, so something like this, where we call it as phi index or W index, sub infiltration index we have seen, right? So what we have seen that whatever we have above this index, we call this as rainfall excess or effective rainfall, right? So why I am reiterating this hydrograph again is the question, right? So now this effective rainfall or excess rainfall, the the discharge that we get from this, or the flow, if you say, the discharge that we get from this, if we plot the discharge versus time. So I was talking about hydrograph, right? So if we plot this discharge in the y-axis and time in the x-axis, then the plot that we get is the hydrograph, or we say it as effective rainfall hydrograph, right? That is ERH. Okay. So, uh, so if you see this hydrograph, how it will be? It will be something like, change the color again. Yeah. So let's say if this is the time and this is the discharge or flow, whatever you say, discharge in meter cube per second. Okay. So how it will be? It will be something like this. Okay. So we'll discuss that what is the rising limb, recession limb, and all. Okay, just to know that it looks something like this. So this plot that you can see is the hydrograph. Okay, so we have also seen. So what is this? This is discharge versus time, right? So we have seen that the runoff that we are getting, that we have studied in the last class or last tutorial session, in that we have mostly discussed about the runoff, and before that we have discussed about the stream flow, right? So we have also seen that the total discharge that we get is the addition of the base flow and the runoff. This runoff and base flow, both of this comes from this rainfall excess or effective rainfall, right? So the total, the area under this effective rainfall hydrograph that you will get is the direct runoff volume, right? So let's say if you just get the area under this, the area under this will be the volume or runoff volume, and if you, because we are considering the base flow also, so it will be runoff volume plus base flow volume. Okay, so this is for the total. Okay, for this rainfall excess or effective rainfall that we are having. Okay, so this is the effective runoff hydrograph. Mm. And many of places we need the direct runoff hydrograph. What is the direct runoff hydrograph? So before going to the direct runoff hydrograph and all, hydrograph, we'll move to hydrograph first. Okay, so I'll explain all these things of hydrograph. So let's say this is the plot of hydrograph. This is discharge in meter cube per second, and this is time. Let's say in hours or days, it can be anything. Okay, and as I mentioned, it will be something like something like this. Okay, so before this also I mentioned that the graphical representation of variations in discharge, it can be stage also, because we have also studied about rating curve, remember. So we have seen that in rating curve it was stage and discharge relationship. So if you just want to know the relationship from the stage point of view, from the rating curve, you can go to stage also. So it can be stage versus time. Okay, so it will be stage hydrograph, if you can say. But this is like it will be variations in discharge with time, right? So let's say if there is one isolated storm. Okay, so only one event of rainfall is happening. In that case, for one isolated storm, how it will be, how this hydrograph looks like, it will be a single peaked, single peaked curve, right? Here you can see there is only one peak here, right? This one. So we have only one single peak. But one more thing that you can see is in the left side the tail is small, so this one, and in the right hand side the tail is much longer. So this means what? This is a skewed curve, right? So it will be single peaked skewed distribution of discharge. Okay. So this hydrograph can also be written as storm hydrograph or flood hydrograph or simply hydrograph. Okay. So why we are after this hydrograph? Why we have dedicated 2 lectures for hydrograph is because see, hydrograph, what it gives you? It gives you the representation of variation in discharge, or let's say stage with time. So with this, what information you are having, that how with time it. So here whatever I have showed is for isolated storm. It can be like 3 4 different storm is different rainfall is happening. In that case also we can create hydrograph, right? So with this, this hydrograph is very important in understanding the dynamics of river system, how the river system works, like at what time, because of some rainfall, some amount of rainfall. We'll study what is unit hydrograph also. So like what duration of rainfall and what rainfall intensity, how it affects the river dynamics, right? So we'll understand from the hydrograph. So for that, hydrograph is very useful. Okay, now you can see from the figure this hydrograph, or let's say flood hydrograph, has 3 main components. So one, okay, I'll change the color again. So here the first one you can see is rising limb. So let's say I'll give some name to this. So let's say where we are starting is A, this is B, this is let's say C, this is let's say P, this is D, or let's say this is E. Okay, now you can see from B, you can see there is one limb that is rising, right? Or you can see the discharge is getting increased. So as the rainfall started, what will happen to the runoff? Because it is a discharge versus time curve, right? So we can call that as runoff also. So as the rainfall is starting, what will happen? Runoff will start producing. We know that first it will infiltrate and then it will go through base flow, evapotranspiration and all. But just after that, what will happen? The runoff will start generating, right? And it will keep increasing. Why? Because rainfall is happening. So in this point from B to C, what we can see that rainfall runoff is getting concentrated, and hence this line, that is VC, is called rising limb because it is having a rise, or it is also called as concentration curve because, as I said, that runoff is getting concentrated here. Okay, so what is the main like representation, or what we can infer from this rising limb is it denotes that how much increase in discharge is happening. So let's say in any catchment area or any region, how the discharge is increasing in response to a rainfall event, right? So during the rainfall rising limb, what happens in both overland flow and channel phases? There is a storage because runoff is creating some storage, right? Next, so this one was first section or first segment. Okay, second component is this, that is crest. So we call this as crest, right? Right, right, to here only. Okay, fine. So second is crest or crest segment. Let's say so crest segment is CD. CD is the crest segment. Okay. So the C and D point, the point C and D are the point of inflection. Point of inflection as in where the slope is changing, right? Okay. And now after D, what happens? So let's say at P, let's P or before P, the rainfall has stopped. Okay. So what will happen? Slowly, the runoff will start decreasing or reducing, right? So in that case, the curve that we are getting, the point, the line DE, this line DE is called the recession limb or falling limb. Okay, you can see this is, well, write it. This is 3, this is 1, this is 2, and this is 3. This is called, this is called recession limb, right? And to note that this recession limb is kind of convex curve, right? So what here, as you can see that what I mentioned, that let's say at point P or before that rainfall has stopped. So as rainfall has stopped, slowly the runoff will start reducing, and because of that, the this curve or this limb, recession limb, on what factors it will okay, on what factors will it depend? Will it depend on the rainfall characteristic? It will not depend on the rainfall characteristic, right? Why? Because rainfall anyway has stopped. Because rainfall has stopped, so there is no point of rainfall here. So only based on what is the basin characteristics. So I'll write that again here. Recession limb is independent of rainfall characteristics. Why? Because the rainfall has stopped, and there is no point of rainfall characteristics. Because if rainfall is happening, then again it will start increasing, right? So it is independent of rainfall characteristic, but it is dependent on the catchment characteristic. Independent, dependent on what I said, basin characteristic or catchment characteristics. So what kind of characteristics? Like how is the soil infiltration capacity, like how fast the runoff can infiltrate. Then it also depends on the slope of the catchment, because let's say if it is more steeper, then what will happen? The runoff can wash away very fast, right? Then it also depends on vegetation cover, or what is the land use land cover of the catchment, and so on, right? So what does this represent? The recession limb. The recession limb will represent the gradual depletion of the stored water. So let's say whatever stored water we had during the rising limb, that will get depleted within the catchment area after the rainfall has stopped. Okay. So this one was like, let's say, the components you can write, right? Okay. So we'll do some questions on this, and then again we'll come back. Okay, before that, let me just go through two more thing. Okay, so as I mentioned that this is because of the rainfall excess or rainfall event that is happening, right? So let's say this is for the rainfall with duration. So wherever you'll see hydrograph, mostly this box will be there. This box will represent the rainfall event. Let's say rainfall event is X, and the horizontal one, it will show you the duration of the rainfall event, and this vertical will show you the depth of rainfall or rainfall depth. Okay. Okay. So, so there are some key elements that you can see in the flood hydrograph. Firstly, it is the storm duration. What is the storm duration? Storm duration, you can see this duration that I mentioned here is the storm duration. Okay. So this is TR, let's say TR, or we can write it as T also. So this is the storm duration. As I mentioned, what is storm duration? Storm duration or rainfall duration, it is the duration of the effective rainfall or the rainfall excess, right? So here we can see whatever duration is happening for the rainfall excess. So it is, so in the hydrograph you can see, right, the black dashed line, that is the rainfall excess. So the total duration of this effective rainfall or the rainfall excess, whatever you call this excess rainfall, is the runoff that produces the hydrograph, right? So the duration for this will be called as the storm duration or rainfall duration. Next, we have time lag or basin lag. Okay, what is this time lag or basin lag? So from the center of the mass of as because this is a rectangular box, the center of mass will be in the middle, right? So the center of mass of the rainfall axis of this to the distance of center of mass. So let's say here you have the center of mass for this curve. Okay, so the distance between this will give you the time lag or basin lag. Okay, so this is time lag or basin lag. Okay, I hope it is clear. But what is time lag? Time lag or basin lag uh, is the time from the center of mass of the rainfall excess to the center of mass of the hydrograph. Okay. Next is time to peak. So time to peak is easy. So here we can write TP. So the time at which the curve or the hydrograph attains the peak discharge, we call it as time to peak. So TP is the time to peak, and the discharge that you get at time to peak is the peak discharge. This is also one of the key element, that is we denote it as QP or something like that. Okay, and next we have time base. So the total time that we have from the start of the rainfall excess rainfall event to the end of the hydrograph, we call this as time base. Okay, time base we generally write it as TB or T. Okay, okay. So with this, we'll go to the questions. The next thing is the factor. Sorry, what happened? Okay. Next thing was factors effective hydrograph. Okay, so the factors affecting hydrograph are very same as that we have discussed in the last tutorial session regarding the factors that affects the runoff, because it is discharge versus time or runoff versus time, right? So the factors that affects the runoff directly or indirectly, it affects the hydrograph also. So I'm not discussing that how which factors are affecting the hydrograph. And you can just go to the lectures and you can find it. So we'll move on to the questions. Okay, so the first question that we have, the question is, a hydrograph is a graphical representation of, it's very easy that we have done so many times. So the correct answer will be rainfall intensity versus time, right? Correct answer will be A. Okay. Next question is, using which parameters hydrographs are constructed? So we know hydrograph is the plot between discharge versus time, right? So the correct answer will be between this stream discharge versus time versus area, distance versus time, stream discharge versus area. So it is stream discharge versus time. Okay, so correct answer again is A only. Next question is the point of a hydrograph, which represents the maximum amount of water that has been stored in the catchment. As I mentioned, you remember that. Okay. So let's say we got the hydrograph. So this is discharge versus meter cube per second versus time in hours. Something like this, right? So the point of hydrograph, which represents the maximum amount of water that has been stored. So remember this, while I was mentioning the rising limb, I mentioned that rising limb represents the amount of water that is stored in both overland and channel phases. So as rainfall is happening, the water is getting stored, or water is flowing as runoff, or water is stored as both this overland flow or channel phases and all. So the maximum point that we have will be the point of inflection, because after point of inflection the storing will reduce, because see, in rising limb it is getting stored, and at the point of inflection it is stopping, right? And after that it start, for some time it will increase, and then it will reach the peak discharge or the crest point, and then again after some point it will start reducing. Okay, so the correct answer will be point of inflection. Okay. So the next, so remember, see, as it remembers the maximum amount of water that has been stored. The whatever after this is there, it is because of the flow that is happening. Okay. Okay. Next question is the shape of the recession limb of a hydrograph depends on. So just now I mentioned that why this recession limb happens, or the falling limb happens. This happens after the rainfall event stops, right? So as the rainfall event stops, then only this recession limb starts. Okay. So as rainfall is not there, so firstly it is not depending on the rainfall, or it does not depend on the storm characteristic. So B gone. Okay. Basin as well as the storm characteristic. So it does not depend on storm characteristic in any way. So A is gone, 2 is gone. Next is basin characteristics only, or base flow only. Okay. So the correct answer will be basin characteristics only. Okay. So the correct answer will be C. Okay, so the next question is the lag time of a basin is the interval of time between the centroid of rainfall and dash of the hydrograph. You just tell me what will it be. Okay, so here it is mentioned like the lag time of a basin is the interval of time between the centroid of the rainfall and the peak of the hydrograph, but it is not the peak of the hydrograph. It will be peak of the hydrograph only when it is like 50% on this side and 50% on that side. As I mentioned, it will be the center of mass of the hydrograph. It will be center of mass of the hydrograph. Center of mass can be the peak point, but for special case kind of thing. Okay, so in this option, if you say like peak, recession limb, base flow, and point of inflection, in that case, peak is the correct answer. Okay, but in general case, it will be the center of the rainfall to the center of the mass of the hydrograph. Okay, so the correct answer for this will be A, but general case, it will be the center of mass. Okay. Okay, so the next question is over a period of time, a watershed got transformed from rural to urban. the effect of urbanization. So what it is mentioned, like for a period of time, so the some time has passed, a watershed has got transformed from rural to urban. So before it was rural, and now it is urban. Let's say the effect of urbanization on storm runoff hydrograph from the watershed is to dash. Okay, I'll give you 1 minute for this. Okay, if you guys can't speak, you can just write in chat box also if you want. Okay. So as I mentioned, the factors that are affecting the runoff that we have just studied in the last tutorial or in the last week lectures also, that will only affect the uh, runoff, and hence it will affect the runoff hydrograph, right? So what is this? Like if urbanization happens, then how it will affect the storm runoff hydrograph? So because of this urbanization, what will happen to the watershed? So we know that if, let's say, when urbanization happens, then what happens? Urbanization will lead to more impervious layer, right? And this impervious layer, what it will create, whatever rainfall is happening, it will not infiltrate and all. Mostly the water that is coming will flow as a runoff. So hence, if it was rural, then what will happen? The water that was coming in the form of rainfall, it will be infiltrating some part, and then some part will be flowing as runoff, right? But in this impervious layer, what is happening? The rainfall is runoff is getting increased because there is no way that it can penetrate through the soil, and hence the runoff increases. Now you see, first option is decrease the volume of runoff. It won't, because as I mentioned that if urbanization happens, then volume of runoff will increase. So this is one. Next is increase the time to peak discharge, right? So peak discharge was, so when it was rural, in that case what was happening, that uh, the runoff or the peak runoff was happening at some later time because the runoff volume is less. Now urbanization happens, so the runoff peak will be very soon, and hence the time to peak discharge will be faster, and hence it will increase the time to peak discharge. We'll just see the other options also. Decrease the time base. We know what is time base, we have just seen. Let's say if this discharge, I'll write it as q, right? And this is time. Then we have seen it will be something like this, okay? And the time to base is, or time base is from the event starts to the end of the event. This is the time base, right? Now it is saying that if it changes from rural to urban, then it should decrease the time base. It won't, because the time base will increase as urbanization happens, right? Next is decrease the peak discharge. Peak discharge, obviously it will not decrease, so hence the correct answer will be B. That is, sorry. Okay, okay, sorry. Oh, oh. Hmm. Okay. So increase the time to peak discharge. So as the runoff volume has increased, uh, the time that will it will take to reach the peak that was happening during the rural time, it will be very fast, and hence it will not increase the time to peak discharge. Next we have decrease the time base. See, if okay, if If it happens that it has urbanization, then how this hydrograph will look? It will look something like, I'll change the color, something like this, right? Something like this. So you see the time to peak discharge has reduced. So time to peak discharge is from the rainfall event to when it is reaching the peak. So it has reduced. So this is for the rural and this is for the urban. Okay, you can see the time base has reduced because from here to here it is now time base for rural, and this is time base for urban. Okay, so the correct answer will be C. Next question is unit hydrograph has one unit of. Okay, so now it is unit hydrograph. So we'll just start from the unit hydrograph only. Okay, so we'll start. What is unit hydrograph? Okay, before that, we have also seen the base flow separation method. So before unit hydrograph, we need to know what is base flow separation. So we have seen in the hydrograph or the flood hydrograph that it starts from like this, right? So the component that you can see in the flood hydrograph, it also includes the, sorry, wait. It also includes the base flow contribution, right? So if we remove the base flow contribution, so let's say if this is the, for example, I'm just saying, if this layer, this discharge is due to the base flow, let's say, then if we remove the base flow, then the plot or then the graph that we'll get will be the direct runoff hydrograph. Okay, so it will start from here, something like this it will go, right? So this will be direct runoff hydrograph. So to get the direct runoff hydrograph, we need to separate the base flow. And we have seen in the lecture there are several methods like straight line method, where we just join the starting point of the rainfall event B to the ending point of the event, that is BE, and then we just remove that as base flow. So that is straight line method. Next we had fixed base length or concave method, right? Then we had variable slope method. So we have seen all these methods, so I'm not going into the detail of the methods. And then constant slope, or let's say constant area method. Okay, so what is the main purpose of doing base flow separation? Main purpose is to distinguish and isolate the base flow component from the total runoff so that we can get the direct runoff hydrograph. Okay, so whatever we are getting from the, so this direct runoff hydrograph is due to the rainfall excess or effective rainfall. Okay, for the total rainfall event, we are getting the base flow plus the direct runoff hydrograph component. But this direct runoff hydrograph is only because of the, I have mentioned somewhere. So here you see the discharge versus time, the total discharge versus time that you can see gives you effective rainfall hydrograph. But the direct runoff hydrograph is for the excess rainfall. Okay. So both, I'll write it here. So both the effective effective rainfall hydrograph and direct runoff hydrograph. Okay, it represents the same runoff volume. Okay, therefore we can write that area under the effective rainfall hydrograph into the catchment area multiplied by catchment area will equal to the area under the detect runoff hydrograph. Okay, this one will help you a lot. Okay, so with this we move to unit hydrograph. Okay, unit hydrograph is a very important component which we study in hydrology or in water resources engineering. So first I'll define what is unit hydrograph. So what is unit hydrograph? See, we have these two terms, that is unit and hydrograph. Okay, so first I'll write the definition. So unit hydrograph is the hydrograph of direct runoff resulting from one unit depth. So this one unit depth can be any, like any unit of what it should be one. So it can be 1 centimeter or 1 millimeter or 1 inch, anything, but it should be one unit. Okay, of rainfall excess or effective rainfall occurring uniformly over the basin and at a uniform rate for a specified duration, and be DRs. Okay, so many a times we see the unit hydrograph as something like, sometimes you will see 3 hour unit hydrograph, 4 hour unit hydrograph. Okay, so it does not, this unit does not depend, give on this uh, duration of the rainfall. Okay, so this 3 or 4 you can see is the duration of the rainfall event. Okay, so what is unit hydrograph? What is unit in this hydrograph is it results from 1 unit depth of rainfall excess. So let's say if 1 centimeter of rainfall excess is occurring over the whole catchment uniformly and at a uniform rate, then we call that as unit hydrograph, or the direct runoff hydrograph that we get from 1 centimeter of rainfall excess, which occurs uniformly over the catchment at a uniform rate, and it happens for a specified duration. So it can be DR's duration, as I mentioned, it can be 3 hour unit hydrograph, 4 hour unit hydrograph, and so on. Okay, so why we are after this unit hydrograph? What is the, like, why? What is the application of this? So this development of flood hydrograph from extreme rainfall magnitude. So we use this in the design of hydraulic structures. Okay, so so one is this development of flood hydrograph from the extreme rainfall events, right? Next, we also can use this unit hydrograph to develop the flood forecasting or warning system based on the rainfall data that we have. Okay, or we can do, so one is the prediction or forecasting. Next we can do what we say is the extension of the records. Okay, so let's say if you have a flood flow record for some years. Okay, so with the, and you are having the same rainfall event, not same rainfall event, a rainfall event with a specified duration. So let's say if 3 hour unit hydrograph you have for the same region. Okay, in that case, let's say again 3 hour unit hydrograph, you 3 hour unit hydrograph or 3 hour extension of flood flow you want. What you can do, you can use the same unit hydrograph to extend the flood flow records that you have for that catchment. Okay, so this is one of the very important thing that we need to know. Okay, so here in this definition also you can see that there are few limitation, and that limitation, one or two you can see here only. That what is the, I mentioned that whenever you are doing some derivation or whenever you are after some concepts, you should know that what are the assumptions that are made in that concept or in that derivation, so that you can know that where it should be applied and so on. Okay. Now in unit hydrograph theory, we know, here you can see it should be uniformly, the rainfall axis that is happening, it should be uniform throughout the basin. Okay, this is one of the assumption. So the rainfall axis should be occurring uniformly over the catchment. Okay, so within whatever specified duration it is. Next, the rainfall event should happen at a uniform rate. Okay, so these two are one or two some assumptions. Then some more assumptions are that the time base or base time that you can see, we have discussed that the what is base time, the time from the start of the event of the hydrograph to the end of the hydrograph, we call that as base time. So the base time of the direct runoff hydrograph due to an effective rainfall of unit duration is constant. So this, for a direct runoff hydrograph, due to an effective rainfall of number unit duration. Okay, unit duration, it can be 1 hour or something like that. Unit duration is constant. Next, the very important assumption of unit hydrograph is that that this unit hydrograph will reflect the basic effects of various physical characteristics of the basin, but it does not change with time. So, if there is any change in the basin characteristic of, if there is any change in the change in the basin characteristic or rainfall characteristic with time, then we can't use this unit hydrograph, but we have to do something so that we can reach to that. So, it considers time invariance. Okay, and next we have the response, like any response we are getting from the drainage basin, it should be linear. So this means that the, so I'll write linear response. Okay, with linear response, what I mean with linear response, I mean that the principles of superposition principle of superposition and also the principle of, okay, I'll write principle of superposition and principle of proportionality, this should be applicable. Okay, so principle of superposition, we can add up the hydrographs of, let's say, similar duration rainfall events. Okay, and principle of proportionality, it is like if the duration of the effective rainfall is fixed, let's say, so let's say if it is like 3 hour unit hydrograph, but its volume changes, then the duration of the direct runoff does not change. Okay, so okay, I'll write that principle of proportionality. So here you see, let's say you have a rainfall event of d duration. Okay, this is discharge versus time, and the direct runoff hydrograph is something like this. Let's say, okay. Now see, what I am saying is, so let's say what I mentioned. This is the duration, and the vertical one, this one, is the depth, right? Rainfall excess depth. So let's say this is 2 units. Now, if the unit of this depth is changing for the given duration, okay. So let's say now it became, this became 1 centimeter. Okay, this is Q, this is T. The same duration we have. Duration is T. Okay. In that case, what will happen? The ordinate of the direct runoff hydrograph will change, not the duration. Okay. So here what is happening? Volume of the effective rainfall is changing, right? Effective rainfall duration is fixed, but volume is changing, which we can see here, right? So what it will respond, the ordinates changes in proportion to the volume of effective rainfall. Okay, so we'll see this in one of the MCQ also. And as I mentioned, what is principle of superposition? So let's say if you have similar kind of unit hydrograph, let's say with a lag, let's say, then what will happen? The principle of superposition says that you can just add them up and you will get a new unit hydrograph. Okay, I'll write as superposed unit hydrograph. It's Q versus T. Okay, so can you tell me what are the limitations of this unit hydrograph? So we have seen several assumptions here, right? So these assumptions itself, if it is if it does not follow this assumptions, then it will not be valid, right? So these are some of the limitations. And also unit hydrograph used for 200 hectares area to around 50 to like 5 lakh hectares. So like it has a huge application, but still, uh, other than this range, we can't use the unit hydrograph. Okay. So how we construct this unit hydrograph? We take the past records of the isolated storm, which is uniformly distributed over the basin, as like what all assumptions we have mentioned. We take that in care, and then we plot the storm hydrograph for the storm. And now we have the this graph, this storm hydrograph or flood hydrograph. Now from this we separate the base flow from any of the method that we have seen before. Okay, like we have mentioned, right? Any of this method, and then we separate the base flow. So what we get the direct runoff hydrograph. So we determine the direct runoff ordinates by subtracting the ordinates of base flow from the storm hydrograph, and then we get the direct runoff depth. And how do you get the direct runoff depth? You can just divide the direct runoff or the total of the direct runoff ordinates, the summation of direct runoff ordinates divided by the catchment area. And from there, what you will get? You will get the direct runoff depth. And from the direct runoff depth, you can calculate the unit hydrograph by dividing the direct runoff hydrograph ordinate by the direct runoff depth. Okay, so we'll see some questions on this. So we have seen principle of superposition and all in the class, so I'll not go to the methods here. Okay, we'll just directly jump to the questions. Sorry. Okay, so we'll wait till here. Okay, so the next question is, a unit hydrograph has one unit of what? I mentioned it should not be the rainfall duration or time to direct runoff. It will be the direct runoff. Okay, so a unit hydrograph has one unit. It can be 1 centimeter or 1 millimeter or 1 inch of direct runoff or rainfall excess or effective rainfall, as mentioned. Okay, so the next question is, 1 centimeter of excess rainfall occurs in 2 hours. So what is mentioned that 1 centimeter of excess rainfall occurs in 2 hours. So the duration of the resulting unit hydrograph is how much? So you can see here we have unit depth only, right? So unit depth happens at whatever rainfall, at whatever duration, we call that as that hour unit hydrograph, right? So here this will be called as 2-hour unit hydrograph, right? So the duration of the resulting unit hydrograph will be 2 hour only. Okay, so the correct answer will be C. Okay, so the next question is, can you read this? Okay. You read this question. So the question is, the unit hydrograph can be used to derive the hydrograph resulting from any amount of excess rainfall, correct? Which of the following assumptions are considered in the in this simple linear model. So it is mentioned that it is simple linear model. Okay, I'll give 1 minute for this. Okay, so what is mentioned, the unit hydrograph can be used to derive the hydrograph resulting from any hydrograph, any amount of excess rainfall, fine. Which of the following assumptions are considered in this simple linear model? So the first question, first option is the excess rainfall is uniformly distributed throughout the whole drainage area, right? So obviously we know that the excess rainfall should be uniformly distributed. This is one of the assumptions that we have just mentioned. Next is the ordinates of all direct runoff hydrographs of a common base time are directly proportional to the total amount of direct runoff represented by each hydrograph. So what it is mentioning, that direct runoff hydrographs ordinates with same base time are directly proportional to the total amount of direct runoff represented by each hydrograph. So this is the principle of proportionality, right? So this is also applicable. This is also proportionality. This is also one of the assumptions. Next, for a given watershed, the hydrograph resulting from a given excess rainfall reflects the unchanging characteristics of the watershed. Okay, so this is also correct. So correct answer will be all, right? Okay. So the next question is a triangular direct runoff hydrograph due to a 6-hour storm in a catchment has a time base of 100 hour, okay, and a peak flow of 40 meter cube per second. The catchment area is 180 kilometers square. The 6-hour unit hydrograph of this catchment will have a peak flow in meter cube per second. So you need to find out the peak flow for a 6-hour unit hydrograph. Just try once. I'll give 2-3 minutes for this. If you guys are getting answer, let me know. Okay, so I'll also do. You guys got the answer. So what we have a triangular direct runoff hydrograph. Okay. So if you just plot the direct runoff hydrograph, it is in the form of triangle, let's say. It is in meter cube per second as mentioned in the problem. This is T in hours, right? And it is mentioned that it is in triangular in shape. I hope the triangle is perfect. Imperfect. Okay. Now what it has mentioned, so this is the direct run of hydrograph. We have uh, the triangular direct run of hydrograph due to 6-hour storm. So we have a 6-hour storm, and a catchment has a time base of 100 hours. So time base, we know it starts from the starting of the event to this. So it is 100 hours, or we can write here it is. Okay. So here we have 100 hours, right? This is 0. Yeah. And a peak flow of 40 meter cube per second. So this is 40, right? The catchment area is given, let's say A is 180 kilometer square. Okay. We'll write the time to peak as, or the peak discharge as 40 meter cube per second. 40 meter cube per second. And what we have, okay, so we need for 6-hour unit hydrograph only, so we don't need to change the unit hydrograph. We have also seen that how we can get the unit hydrograph of different durations or something like that, right? So how we can calculate the direct runoff depth? It will be the direct runoff volume, so it will be half. So the total area under this will give you the volume, right? So half into 40 into how much is the time? 100. So this 100 is in hours. We'll change this to seconds, and the area we have is 180 kilometers square, right? We'll change this to meter square. Okay, you just do this, how much you'll get? Something like 0.04 meter, that is 4 centimeter, right? So we got the direct runoff depth of 4 centimeter. Now what we need the peak flow. So peak of the unit hydrograph, or 6-hour unit hydrograph, will write 6-hour unit hydrograph will be the peak of direct runoff hydrograph divided by the direct, write this as DRT, let's say, okay, direct runoff depth. So that will be equals to 40 divided by 4, that is 10 centimeter. Okay, oh sorry, 10 meter cube per second, because it is 10 meter cube per second, right? So the correct answer will be A. I hope this is clear. If you have any doubt, any question on this, you can ask. No? Okay, we'll move to the next question. Okay, so the next question is, unit hydrograph theory is based on the following assumption. Uh, in this, non-linear response, no, because we know it is a linear response, right? So, okay, and it should be time invariant. So the correct answer is D, that is time invariance and linear response. Okay. Okay, so the next question is, the lines that depict areas of approximately equal travel time are known as, so we have seen this before previous lectures, as just mentioned. So it would be isoclones. Okay, iso heights we know of equal rainfall intensity, isobars equal pressure, and so on. So correct answer is C. Next question is for a catchment with an area of 360 kilometers square, the equilibrium discharge of the S curve. Okay, so before that we mention what is the S curve. Okay, so S curve comes from here. That is when you need the unit. So you have, let's say you have one unit hydrograph for some duration. Okay, so and you need the unit hydrograph of different duration. Okay, we have also seen the unit hydrograph, that how you get unit hydrograph from, if you have different rainfall, not isolated storm. It can be different storm with different depth, rainfall excess depth, and from there how you can get the unit hydrograph. Okay, so methods and all I'm not going. But let's say if you want the unit hydrograph of different duration, in that case, if you want to derive the unit hydrograph, then what is there? So let's say if you have a 4 hour unit hydrograph, okay, 4 hour unit hydrograph you have, okay, and you need a 12 hour unit hydrograph, right? Then you see, if you see this, what we have, this, the need, the unit hydrograph that we want is of 12 hour duration, right? So this 12 is a multiple, is a integer multiple of 4, right? So as this n, we can write n is the proportion of the one which we need, the one we have is 3. So this is what, integer value, right? So in that case we can use the method of superposition. So how we will use the method of superposition? So here we have 4 hour unit hydrograph and 3 lags will take, and then we will just add all those, or we'll just superimpose all the unit hydrograph ordinates, and then we'll get the 12 hour unit hydrograph. Again, if you, here what we are doing, 3 hour lags we are giving, but for 3 times, right? Or 3 you are giving, so 1 centimeter each, so we have to divide it by 3 centimeter, and then you will get the 12 hour unit hydrograph from there. Okay, this is another one. Now let's say if this n is not integer, you have the 4 hour unit hydrograph and you need, let's say, 2 hour unit hydrograph. Okay, here n is what? Need is 2 and you have 4 hour. So it is 0.5. This is not integer, right? So in this case, you can use the S curve, or we call this as summation curve. Why this is called S curve? One thing is like this starts from summation curve kind of, or it looks like very similar to a deformed S, and that's why we call that as S curve or S hydrograph. Okay, so S hydrograph or S curve is a hydrograph which is produced by continuous effective rainfall at a constant rate for an infinite duration. Okay, so how to get to this S hydrograph and all we have seen in the lecture. We have also seen, like if you just want to know the equilibrium flow, then we can use this formula, that is QE equals 2.78 A by D. This is very similar, like A is the area and D is the depth, kind of. So A is in kilometer square. If you are putting proper units, then you don't need this 2.78 also if you go for hectares and all. So D is in hours. Okay, so from this you can calculate that how much is the equilibrium flow. Again, this QE, it will represent the maximum rate at which an uh, like effective rainfall intensity of 1 by t centimeter per hour can drain out of a catchment of area A. Okay. Okay. So with this, we will go to the question. So this is done. Oh, this is also done. Okay. So for a catchment with an area of 360 kilometers square, the equilibrium discharge for the S curve obtained by the summation of 4 hour unit hydrograph is in meter cube per second, how much you are getting. So just now we have seen for equilibrium discharge QE, we can write it as 2.78 into A by D, where A should be in kilometer square, that is 360 kilometer square, and the D is 4 hour unit hydrograph, which should be in hours only. So just put this 2.78 into 360 by 4, you get something like, okay, I'll just calculate. Okay, so it is coming as 250.2 meter cube per second, right? So the correct answer will be A, that is 250 meter cube per second. Okay, this was clear, right? Okay, so the next question is the correct sequence of the following steps involved in arriving at unit hydrograph. So the steps are estimating the surface runoff in depth, estimating the surface runoff in volume, separating of base flow, and dividing the surface runoff ordinates by depth of runoff. Okay, so the first thing that we have to do in these steps was to separate the base flow from the direct runoff hydrograph, right? So after separating the base flow from the storm hydrograph or flood hydrograph, from there what you will get? You will get the direct runoff ordinates, right? Then what you have to do? You have to estimate the surface runoff in volume. Now, after you know this surface runoff in volume, you have to estimate the surface runoff in depth, and then from there you can just divide the surface runoff ordinates by the depth of runoff, and then you will get the unit hydrograph. So this is 1, so it will be 2, this is 3, and this is 4. So the correct answer will be 3, 2, 1, and 4. So the correct answer will be A. Okay. I hope this is clear. Any doubt? Okay, we'll move to the next question then. If two 2 hour unit hydrograph are staggered by 2 hours and added graphically, the resulting hydrograph will be what? So, what we have? So, let's say unit hydrograph Q, and T. You have two 2 hours unit hydrograph like this, then again something like this, right? Now, what they are saying that it is added graphically, so something like this you are getting, right? So the resulting hydrograph that you will be getting. So here we are just taking the 2 hours unit hydrograph, which is staggered by 2 hours. So let's say this is 2 hours. Okay, and again this is 2 hours of unit hydrograph only, right? So we have 2 hours unit hydrograph. Okay, now we are adding that graphically. So this is the superposed unit hydrograph. Okay, so how much so what will be the firstly what will be the unit hydrograph? It will be 4 hour unit hydrograph, right? Because two hours are there. 4 hour unit hydrograph, and again 1 centimeter of this, because what is unit hydrograph? Unit hydrograph is of unit 1 unit depth, right? So it will be, this is 1 centimeter and this is also 1 centimeter, so the total will be 2 centimeter. If you divide this by 2 centimeter, then you will get the 4 hour unit hydrograph, but the one which you will get is 4 hour unit hydrograph but with 2 centimeter runoff. So the correct answer will be D. Okay, any questions? Okay, so we'll move to the next question then. S curve hydrograph is the hydrograph, so we know this. Anyone, any guesses? So the correct answer will be, sorry, correct answer will be B. That is here. So the correct answer will be B. That is, S-curve is hydrograph is a hydrograph of flow from a 1 centimeter intensity rain of infinite duration. Okay, because we just superimpose everything and then we get the S-curve. Okay. Next question is, the peak of 5 hour unit hydrograph of a catchment is 150 meter cube per second. The peak of 10 hour unit hydrograph of the same catchment will be what? So if you would have seen the lectures properly, or if you have observed the problems that you have solved during the lectures, you can answer this question. So see what you have. You have a 5 hour unit hydrograph. Okay, so you have a 5 hour unit hydrograph, and the peak QD QP you are getting as 150 meter cube per second. Okay. Now I am asking for 10-hour unit hydrograph and what will be the peak for it, right? Can anyone guess, or I'll give you 1 minute for this. Just let me know what you think. You can just write in the section very well, right? So what we can do here is, so you have 5-hour unit hydrograph. So let's say you have the unit hydrograph ordinates. Okay, so you have the unit hydrograph ordinates. So it's like time is in hours, 0, 5, 10, 15, 20, 25, something like that. Okay, unit hydrograph, you have some value, let's say 0, something on the 2, 5, just example. Okay, 1, 2, 5, 7, 3, 1, something like that. Okay, now for 10-hour unit hydrograph, what you have to do, you have to give a lag of, this is 5-hour unit hydrograph. Now 10-hour unit hydrograph, what you have to do, you have to give a lag of 10 hours. Okay, and then it will start again, 0, 2, 5, 7, 3, 1, something like that. Okay, now if you just add and divide it by 2, if you do it for any given unit hydrograph from any problems that you have, if take any problem from the lecture, and if you just do, you will see that when you are changing this 5-hour unit hydrograph to 2-hour unit hydrograph, sorry, 10-hour unit hydrograph, and just get that, what you will get the peak hydrograph or peak of the this hydrograph as less than that of 150 meter cube per second. Okay, so the correct answer will be less than 150 meter cube per second. Correct answer will be C. Okay, because we have the proportionality principle, right? Just use that in formula. Okay, so the next question is 5-hour effective rainfall of 12 centimeter over a catchment produced a peak runoff of 600 meter cube per second, right? Over the same watershed, another 5-hour effective rainfall of 4 centimeter produces a peak flow of dash. Okay, so the first is 5-hour effective rainfall of 12 centimeter. This is the effective rainfall depth, and peak runoff is 600 meter cube per second. Again, same effective rainfall happening, but the depth is changing, it is 4 centimeter. Then what will happen to the peak flow? So from the first, you can get the unit hydrograph. So 5-hour unit hydrograph will be how much? 600 by 12. That is how much? What punch side? 50. Right? Just do it. Then once. Right? It will be 50 meter cube per second. Right? Now you have the same 5-hour unit hydrograph, but for 4 centimeter. Right? So no, here we have 4 centimeter. So it will be direct out of hydrograph. Sorry. So the direct runoff hydrograph peak due to an effective rainfall of 4 centimeter will be equals to 4 centimeter into the unit hydrograph, because unit hydrograph coordinate you have, you just multiply using that, you will get a 200 meter cube per second, right? So the correct answer will be B, that is 200 meter cube per second. Any question here? Okay, so we'll move to the next question then. Find the equilibrium discharge for the S curve hydrograph obtained from a 3-hour unit hydrograph and the catchment of 270 kilometers square. I'll give 2-3 minutes for do this. Let's do this. Okay, so I hope you guys got the answer. If not, we'll do it. So what we have, we need to find the equilibrium discharge for the S curve, right? So just you use the same expression again. So just calculate. We have 89 kilometers square. 3. Yeah. So we have equilibrium discharge Q is equals to 2.7 something, 2.78 something, right? How much it was? 2.78 80. 0.78 into A by D, right? And you remember this was 1 in kilometer square and this should be in hours. You just need to use this 2.78. So 2.78 into how much it was? 270 kilometers square and it was 3 hours. So 2.78 into 270. It's coming as 250.21. Okay. So the correct answer is 250.2. Range I have given some range. Okay. Okay. So we'll move to the next question. I hope this is clear. So the next question is the 6-hour unit hydrograph of a catchment having area of 1200 kilometers square can be approximated as a triangular unit hydrograph again. Okay. So we have a triangular unit hydrograph with a base period of 8 days. The peak flow in the direct runoff hydrograph of this basin produced by an effective rainfall of 5 centimeters in 6 hours is equal to how much? I'll again give 1-2 minutes for this, just at least start. So first find the peak discharge. I'll do with you guys, let's say. Okay, so the peak discharge of unit hydrograph, how much will you get? 6 unit hydrograph. It will be, because it is a triangular unit hydrograph, right? So half into base is 8 days. The peak discharge is how much? 12, sorry, how much? Okay, so peak discharge and we have to find out. So let's say peak discharge is QP, and this is in days. We'll convert this into second. 24 into 3600, right? So the peak discharge, sorry, this is not peak discharge. Okay, so we need to find the peak discharge, right? So okay, this will be equals to this will be the area under the curve, right? So let's see if you have the unit hydrograph. This is Q, this is T, this total is 8 days, this is in days, right? And this is a 6 hour unit hydrograph. Okay, so we can write the area under the curve for the unit hydrograph into the depth of the effective rainfall will be equal to the area of the direct runoff. So we can write it as 1200 is the total catchment area, right? 1200 kilometer square. So we'll just change this to meter square. If you need in centimeter, we'll just divide by 100. It will be half into 8 into QP into 24 into 3600. Just calculate how much you are getting QQ. I'll also calculate. You can just see. We'll write it as 1200 plus 6 into 2 500 into 8 into 24 into 3600. So I'm getting something like 34.72 meter cube per second. Okay. Now what we need the peak flow in the direct runoff hydrograph for effective rainfall of 5 centimeters. So how we can find therefore the peak flow due to 5 centimeter effective rainfall will be equals to depth into the peak discharge that you are getting from unit hydrograph, right? It will be 34.72. Let's multiply how much you are getting. 173.61 meter cube per second. So this will be the answer. I hope you guys are also getting the same. Okay, so the range is in 170 to 175 meter cube per second. Okay. Okay, so we'll move on to the next question. So the next question is the ordinates of 2-hour unit hydrograph of a catchment is given below. Okay, so we have a 2-hour unit hydrograph with these values. The catchment is experienced by the following storm. So we have different storm. Okay, it's not isolated storm. So here we have accumulated rainfall. Remember, the phi index for the storm is 0.2 centimeter per hour. Assume the base flow to be 15 meter cube per second. The peak runoff in a catchment is how much? That just think how to do. We'll just start. I'll do after 1 minute. At least you guys can start. Okay, so I'll start now. So from this hydrograph first we'll start. So we have time in hours. We have the accumulated rainfall. In centimeter, right? So it is 0, 2, 4, 6, 0, 4, 6, 10. So this is the accumulated rainfall, right? So how much will be the incremental rainfall or rainfall in each 2 hours? So first anyway it is 0, 4 minus 0 it will be 4, sorry, right? And 6 minus 4 it will be 2, and 10 minus 6 it will be 4. Okay, so we have the incremental rainfall, and how much will be the effective rainfall? We can write effective rainfall as the incremental rainfall. Let's say I will write it as R I. So Ri minus phi into del T, right? So how much is the del T for each of the time? You can see it is 2 hours, right? So first one will be 0 minus 0.2 into 0. It will be 0 only. Is 4 minus 0.2 into 2. 1, 4, 3.6. 2 minus 0.2 into 2. 0.4, 1.6. And 4 minus again 0.2 into 2, that is 3.6. Okay, so we have got the effective rainfall now, right? Next, we need to calculate the ordinals. Okay, so we'll do in the next page. So we have time in hours, right? And we also have the 2-hour unit hydrograph. Okay, so we need to calculate what? We need to calculate the direct runoff hydrograph. Okay, direct runoff hydrograph for different rainfall, effective rainfall, that is 3.6, 1.6 and 3.6. Okay, okay, so I'll write this 0 to 22. Okay, 0, 4, 6, 8, 10, 12, 15, 16, as many as there, 16, 18, 20, 22, right? And the value was 0, right? Now for first one was effective rainfall was 3.6 centimeter. I'll just like this. And for effective rainfall of 1.6 centimeter. And then for effective rainfall again for 3.6 centimeter, right? Yeah. So for the first 2 hours, it will be at the same. It starts from the same, right? So okay, so it will be 0. I should have this value calculated somewhere. Let me check. So here what we have the effective rainfall depth, and we have the unit hydrograph value. So we just need to multiply, right? So 25 into 3.6, it is 90. This is 25 into 3.6, like that. 40 into 3.6, it will be 144. Then just find, I'll write that. I have the values: 225, 432, 288, 234, 172.8, 126, 90, 54 and 0. Okay, now we have the next effective rainfall, but that is after 2 hours, right? So we have a lag of, I'll not write here anything, don't put 0 and all. Okay, it is like lag, right? So that's why if we put 0, it means a value of 0, right? So that's why we are not putting. So here we'll start with 2 hours lag. So it will start from here. So 0. Now what you have to do? You have 1.6 step. So you can write 25 into 1.6. It will be how much? It will be 40. Okay, like that you have to multiply with 1.6. It will be 64 and 144, 192, 128, 04, 76.8, 56, 40, 24 and 0. Okay, and next again this is after 4 hours, so lag 2 lag 4 hours, and then this will be 0, 25 again into 1 3.6, it will be 90 and so on. So 90, 144 and 324, 432, 288, 234 and 72.8, 126, 90, 54 and 0. Okay, now what we have to get, we have to get the total flow, right? So total flow will be, so we have a base flow was how much in meter cube per second, it was, base flow was given in the problem, it was 15 meter cube per second, so it will be 15 everywhere, right? And then the total flow will be how much? Total flow will be just the summation of all, right? So if you just add all, 0, nothing is there, then 15, so it will be 15. This one will be in meter cube per second. So 90 plus 0 plus 15, it will be 105. 144 plus 40 plus 0 plus 15, it will be 199. Okay, so just add all this. So if I give the column number, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So 7 will be 3 plus 4 plus 5 plus 6. Okay, this will be 7 column. That will be 493, 735, 819, 809, 579.8, and 451.8, 333.8, 235, 129, 69 and 15. Okay, so now here you can see what was the question, sorry. It will be 15 again, right? Okay, yeah, so what was the question? Question was the peak runoff in the catchment that we need to find. So how much you are getting the peak runoff? So the highest value will be the peak runoff, right? So the peak runoff you are getting as 819. So the correct answer for this will be 819 meter cube per second. Okay. So see, the range is given as 817, 821. Just put somewhere else, but it is visible. That's fine. Okay. So the correct answer is 819 meter cube per second. Okay, so let's move on to the next question. This page is not required. Yeah. So we'll move to the next question. So this is the same question that we have. Just the question here is the time to peak or time of rising is dash hours. Okay. So we have got the peak at 819 as 819 meter cube per second, right? So the time that we are having at this peak flow will be the time to peak, right? So the correct answer will be 10 hours. It will be 10 hours. Okay, so the correct answer will be 10 hours. Okay, after this we don't have any question. Okay, any questions? Any questions, any doubt in this lecture? Okay, if not, we'll stop the session then here.